Let us talk about this problem. We are supposed to implement a class called KStacks. And this class, you should use a single array and it should implement multiple stacks inside the single array. There might be reasons to have it. Suppose you want to use the same space for implementing multiple data structures, and the reason might be cache friendliness or locality of reference, right? If you have everything at one place, your data is more cache friendly, right? You are able to access the items from cache only. So this might be the requirement. So our problem is we are supposed to use a single array and all these stacks should be using the same space, and there should be k-space stacks implemented, and the capacity of this array is CA, which is the size of this array, is its CAP cap. So we are supposed to implement the constructor, which takes the capacity as an argument, number of stacks as an argument. We are supposed to implement a push function that takes stack number as an argument. So stack number has value from 0 to k minus 1, right? And an item x to be inserted in the stack. Pop function, which again takes a stack number and takes out an item from the given stack. IsEmpty function, it tells you whether the given stack number is empty or not. We might have an additional function called top also, which gives you the top of the stack, but for keeping the number of functions low, I'm not writing stop here. And the expected type complexity of these operations are big O of 1 only. This should be big O of 1, this should be big O of 1, this should be big O of 1. So a naive solution, as we have discussed, a two-stack problem would be you divide your whole array into three k parts. Suppose you want to implement 3 stacks, right? So say you have this whole array, you divide it into 3 equal parts, and then you have 3 stacks inside this array, right? The problem with this naive approach is if this stack becomes full, right? Even if you have spaces available in the other stacks, you are not able to use because you have allocated fixed space for every stack. That's the problem with this approach. And consider a situation where this is not an integer array, this is actually a business object, say student, which has a lot of data inside it, right? Student object, a student array or teacher array or any other business object. So this space wastage could be a problem, right? So now please pause this video and think of a solution that uses space completely. If there is even a single available slot, you are going to use it, you are going to allow push operation in any stack. To give you a hint about the solution, we are going to use 2 extra arrays, 2 extra integer arrays, and we are going to use an extra variable to maintain the k stacks, right? So integer arrays are not very costly space-wise also if you have a large object array, right? And these one integer array is going to be of size n or capacity, and the other is going to be of size k. So now I have given you enough hints. Please pause this video and try to write down an efficient approach yourself. Here is implementation of the idea we talked about. We have a KStacks class where we have our array which is going to store the actual items. Then we have top array which is going to store tops of the stacks. Then we have next array which is going to store next item in all the stacks and also in the free stack, right? And we are storing free top separately. We could create an array of size k plus 1 as well, but we chose to create a separate variable. You can implement either way. So k is the number of stacks, capacity is the capacity of this array. We have this constructor where we initialize the k member of this class, where we initialize the capacity. We allocate memory for these 3 arrays. ARR is of size n, next is also of size n, and capacity and top is of size k. Then we initialize top as -1, right? This is our initial setup that we get ready, right? We create array, we create top with -1. And if you take a closer look at the next array, next of 0 is 1, 1 is 2, 2 is 3, 3 is 4, and 4 is -1. There is nothing below the last item, right? So everything is in the free stack and there is nothing below the last item in the stack, below next in the next stack. So we initialize all values as I plus 1 except the last value. Last value is initialized as -1. Let's now talk about the push operation. So push operation takes the stack number and x as arguments. It inserts x item into stack number Sn. Now when you talk about push, you need to take a free slot, right? And I'm not handling those corner cases here in the code where there is no free slot. You can add an extra code. If free top is -1, then show an overflow error, right? So here I'm assuming that you always have a slot and user never inserts beyond the capacity. So what we do, we need to take out a free slot, right? And we need to assign this free slot to the stack where we are inserting the item. and we also need to ensure that next mapping is maintained in the stack where we are inserting and in the free stack as well. So how do we do it? We first get the current free top in index I, right? And we make free top as next of I, right? So free top is changed to the next item in the free block list. So if you take a look at this this setup, when we insert 100, what we do, we take the free top, right? And we know that 0 is the slot where we want to insert the item. So we insert 100 here, right? Now, after inserting 100 here, we need to ensure that we have next of it is set in the stack, because now it is part of this stack number 1. And next of it should be -1 because there is nothing below it. This is the first item. So how do we make sure that next of it is -1? We take the old top value. When we are doing this push operation, we don't know what is next of it, right? It could be -1, it could be some other index. So whatever was the old top value, we copy it to the current free top index, right? We copy it to that free top index, and we update free top as free top dot next, right? So free top, or you can say update free top as next of free top, right? So next of free top is 1, so we update free top as 1. That's all we have done. And the sequence of these operations is very, very important. We first get hold of the current free top before we update the free top. Then we update the free top as next of I, right? We updated it from 0 to 1. We went to this array and used this as an index and got the value 1, so we updated free top. Then we get the next of I as top of Sn. So next of I is, this is updated as -1, right? This old value of top is copied here. Then top of Sn is made as I. So top of this becomes 0, right? The current free to item that we've taken. And array I becomes 6. And then we copy this item 100 here. That's how we push 100 into stack index 1. Let's now see one more example. We want to insert 200 in the same stack, right? So we are going to take a free slot. We get the free top index as I. We go to that index and insert 200, right? Then we need to copy the old top at this index. We copy 0 here. Then we need to update free top as free top dot next. So we got the old value of free top, and using that value we got the next, and we update the free top as 2. All these operations are done here. At the end, we have array I as x. So you can put this operation anywhere. You can do it even after here. So this is how push operation works. Let's now see the pop operation. In the pop operation, we need to remove the top item. So the top of current stack should become the next of the current top, right? So we first get the top of the stack, right? And we then update the top of the stack as next of current top, right? And whatever item you have removed, whatever slot this top was taking, this slot should now be assigned to the free stack, right? So we assign the free top as I, and before that we assign next of I as free top. So whatever previous free top we had, this becomes now next of current free top, and current free top is now I. So that's all we do in the pop operation. At the end we return the top popped item. Let's understand with this example. We want to do pop 1. That means we want to remove 200. So we first get the I as top of 1. Top of 1 is 1, right? So I is now 1. Now we make top of Sn as I. So top of Sn as next of I. Next of 1 is 0. So we make it as 0. Now you can notice that top of this stack is 100 now, right? And then we make next of I as free top. So next of 1 now becomes 2, right? This is current free top, right? And free top now becomes 1. This one slot that we remove, we now make it the top of this stack, right? So this is how pop operation works. Now isEmpty operation is super simple. We are simply checking if top of Sn is -1. If this is -1, then we return true, otherwise we return false. Now if you take a closer look at these operations, they are all big O of 1. This is big O of 1 operation, this is big O of 1 operation, this is big O of 1 operation, right? So we have implemented k stacks in an array with big O of 1 operations each, and we are best utilizing the space. If there is a single space available, we are allowed to do the push operation.